look like. And we saw that that stress block can be calculated using this equation here, and therefore we can actually calculate the stress. Now, if we know the stress and we know the Young's modulus elasticity of a material, we can actually go ahead and calculate the strain. Now, this is the foundation of how cracking is calculated, because we're saying the element is bending. Can we calculate the stress at the surface that is most stressed in tension? Once we can calculate that, then we can go ahead and say, so what is the stress-strain relationship of this material that is concrete? And therefore, then we can proceed to calculate the crack sizes, because we know how much strain concrete can take before cracking. So anything beyond that, then it contributes into the crack. But we will see some detail today on these thoughts. So now we decided to look at an example. We started looking at an example. We said if we were to look at a section whose thickness is 350 millimeters and concrete cover to reinforcement is assumed to be 50 millimeters, and the strength of the concrete is 30 newtons per millimeter squared, the Young's modulus of elasticity of steel, 200,000 newtons per millimeter squared, Young's modulus of elasticity for concrete, short term, is 30,000 newtons per millimeter squared, and the applied moment at ultimate limit state, 234.8 kilonewton meters per meter. And if for this ultimate limit state moment, we need T20s at 125 centers to be able to carry that moment for the ultimate limit state. So then we said, let's assume that the factor of safety is 1.5, the factor of safety that has transformed the moment, the ultimate moment, from a serviceability limit state moment to an ultimate limit state moment. So then I went ahead to try and explain where this particular example would have been extracted from. And hopefully in the next one session or two, we will look at how a box culvert is loaded. Basically, box culvert is amongst the simplest forms of small bridges that you can find. So when a box culvert is loaded, what we sketched here in red is what would occur as bending moments. And I went ahead to then sketch for you on this 3D sketch where the cracking would occur. And that's where we would be interested to carry or to check the crack sizes. I also made a small discussion about where this factor of safety of 1.5 would have come from. And of course, you know that when we have loadings in a building or on a building or a structure, if we want to convert those loads from a serviceability limit state to an ultimate limit state, what would happen is we would put factors of safety onto those loads. Now, I took the simple example of the loads on a building, gravity loads, and the standard, the BS says that to capture the ultimate limit state loading, you simply apply 1.4, a factor of 1.4 to dead loads and a factor of 1.6 to live loads. Now, looking at those two, therefore, approximately the factor of safety into this into the loads on the building would have been 1.5. So that's where the 1.5 came from. And it's actually an estimation. It does not necessarily mean that it is absolutely correct. So then we started doing the analysis, and the first thing that we did was to convert the ultimate limit state moment, 234.8 kilonewton meters per meter, to a serviceability limit state by dividing it by 1.5, which is factor of safety for loads. And we approximate factor of safety for loads, for example. And we found that the serviceability limit state moment would be something like 156.5 kilonewton meters per meter. Just to remind you that we talked about per meter in this sketch here. Why are we saying per meter? Because we consider a meter length of the culvert that way. And we design that, and then we provide for the whole length of the culvert. So then we went ahead to backtrack our steps a bit to where we started from, to say, so where is the neutral axis? Today we will see why we are interested in the neutral axis, that is the depth h. Let me just remind you from this sketch that we had done earlier. So you remember that we did say that we are interested in this dimension here, x. Okay? Now, if the material is perfectly elastic and perfectly isotropic, the dimension x is simply half the height of the rectangular cross-section. If the material that is used to make this element is perfectly elastic and perfectly isotropic, then the value x from your strength of materials will simply be a half of the height of the cross-section. But the material we're dealing with, concrete, itself is not perfectly elastic. It's actually elastic plastic. And then we have put in reinforcements. So again, changing that scenario a little bit further. So we will need to therefore calculate where is the depth of that value x in our section. Where is the value of that depth x in our section? And don't worry, I'll sketch this section for you and we will calculate these numbers, and you will see that it's not a difficult thing to calculate this crack size. So due to the fact, we wrote it, say this to say, due to the fact that the reinforced concrete is not a perfectly elastic material, and also that it is a composite material composing of concrete and reinforcement, the position of the neutral axis x is not necessarily at the center. Please note that I'm using the word not necessarily. So it doesn't mean that it's not always at the center, but it means that sometimes it's not at the center. It's not necessarily at the center. Sorry, this thing sometimes it misbehaves. It's not necessarily. So by coincidence, in some cases you might find that you calculate, you find that the depth of the neutral axis, that is the dimension x, is actually half of the h, but it will be coincidence. It can be greater than h over 2 or less than h over 2, depending on several things. Now, those several things that affect how deep, how far this neutral axis is from either ends of the cross section. Two factors we mentioned: the ratio of the area of the steel to the effective area of the cross section. So, as you put in more steel, the depth of the neutral axis in that cross section changes. As you reduce the amount of steel, that value also, that x, the depth of the neutral axis also changes. So it's the first one. The second one, we also say that the depth of the neutral axis, this is the value of x, is dependent on the ratio of the stiffness of the reinforcement steel to the concrete. So we know that steel is a lot stiffer than the concrete. The steel is a lot stiffer than the concrete. So we're talking 200,000 newtons per meter squared compared to 30,000 newtons per millimeter squared. And this 30,000 newtons per millimeter squared is actually a short-term modulus of elasticity of concrete, and it's actually an approximation because in physical terms, if you think about it, it's non-existent. So now, for us to deal with to calculate the long-term modulus of elasticity, we need to apply a factor of a half to the short-term modulus of elasticity, so that then we can get a long-term modulus of elasticity. That's why this equation of this factor alpha uses ES, but when we come to concrete, because we're interested in long-term modulus of elasticity for concrete, we apply a factor of half. So that's where we reached that other in the previous session, and I want us to now proceed with that recap to I want us to proceed with the rest of this calculation. So we need to find the depth of the neutral axis. To find the depth of the neutral axis. Okay. So x is given by the BS as d into brackets minus rho alpha plus the root of brackets rho alpha squared plus 2 rho alpha, all this under square root, and then the bracket closes there. Now, you notice that the equation that defines the depth of the neutral axis is dependent on these two factors, rho and alpha, which we defined in the immediate previous session. Okay, we said what they are. So we will just go ahead and calculate those values for this particular problem that we're dealing with here. So rho is AS over B D. AS, just to remind you, we were given that in the question, is 2512. 2512 is this number here is AS. So 2512 divided by 1000 by 300. Look, we're looking at this section this way. Let me sketch it here so that you can follow easily. So of course, the wall is continuous. The wall is continuous. The wall is continuous. And just to remind you, allow me to take you back to the 3D sketch we made the previous session. So now we are looking at this wall that way. So we're looking at the 1 meter width strip. We're looking at that distance there. It's 1 meter. Okay, that's what we're looking at. So we're cutting the wall and we're looking at it in so that's how it would look like. Okay. And of course, there is reinforcement that is 2512 millimeters squared per meter. 2512 millimeter squared per meter length. Okay. In this wall, we are considering, let me use the blue that we used to highlight it on the 3D. So we are considering, just to remind us, 1 meter width. We're considering 1 meter width of the wall here. 1 meter width of wall. The dimensions, therefore, would be, we have been told that the wall is 350 millimeters thick. So this dimension is 350 millimeters. And we are considering a 1 meter width strip of wall. So this is basically 1000 millimeters. Okay. Use a darker color here. Darker pen. So this is basically 1000. Now with that, therefore, we can easily calculate the effective depth. Effective depth, D is 350 minus approximately 350 minus the concrete cover, which we have been given as 50 millimeters. Concrete cover to reinforcement has been given in this problem as 50 millimeters. Okay, so approximately the effective depth is 350 less 50. It's 350 less 50. which gives us 300 millimeters, okay, which is this value here. Okay, so now with that understanding, we can go ahead and calculate the value of rho. And my reference calculation here suggests that this is 0.0084, 0.0084. Please, you can check. You can be checking as we go along. Then also we need to calculate the alpha. What did we say the alpha was? The alpha is the ratio of ES over a half EC. So we come down here, we write, this is ES over a half EC, and therefore this is 200,000 divided by 0.5 times 30,000. This gives us 13.33, 13.33. You notice that both factors, rho and alpha, are dimensionless. I'll repeat. You notice that both factors, rho and alpha, are dimensionless because we are dividing, for the rho, we are dividing an area with an area, and for the alpha, we are dividing the modulus of elasticity with another modulus of elasticity. So the units just cancel out. So they're just pure numbers. So therefore, then we can calculate and say, so what is rho alpha? Rho alpha is simply 13.33 multiplied by 0.084. And this, if my working is correct, should be 0.112. Okay, and therefore, the depth of the neutral axis for this section will be the depth of the section, effective depth, into minus 0.112 plus the square root of 0.112 squared plus 2 into 0.112, close all this, and brackets. Okay. You can check that number, but what I got previously was 112.3 millimeters. Now, what that effectively tells us is that the way the section is, it's 350 millimeters total section, so 350. So if it was perfectly elastic and isotropic, then the neutral axis will be at 175. The neutral axis would have been at 175. But now, because this material, the concrete itself, is not perfectly elastic and perfectly isotropic, and also because of the reinforcement, now that neutral axis is actually at 112. Instead of 175, which would have been half of that depth, is at 112. So 112.3. This is the physical interpretation of that calculation. And this, of course, is the neutral axis. Okay, so now we have determined the neutral axis. I'll show you again in the next step why we even bother to calculate the neutral axis. So with that, we can go ahead and find the stress in the steel and in the concrete. We can go ahead to find the stress in the steel and the concrete. Why do we want to do that? Where we started from, Where we started from. We laid a foundation to say if we can find the stress, we can find the strain. If we can find the stress, we can find the strain. So now we want to apply those theories in concrete to find the stress. And I keep deviating from the calculation so that you can understand where these equations are coming from, why we are even bothering to calculate that. So for example, we have spent a few minutes to say why we need to calculate the value of x, the depth of the neutral axis, because the material is not perfectly elastic and it's not perfectly isotropic. So now I want to say to find stress in the tensile reinforcement steel. If we can find the stress, we can find the strain. We can know how much the material is stretching. And from there, we can calculate the size of the crack. So just as a recap of your reinforced concrete design theory, you will remember that you dealt with the beam. Oh my. This thing is stuck. Let's give it some bit of time. Yeah. So you remember that when you designed the reinforced concrete section, of course, you had the neutral axis, which we have now reminded ourselves that it does not necessarily have to be at the center. It's somewhere. Okay, and we've even made an attempt to calculate the position of that for the case of this wall that we are trying to design. So this section here is under compression. Okay, from the reinforced concrete design. We just said that this here is the value of x that we're interested in. Because we have also calculated the effective depth, or we know for a normal reinforced concrete element, we define the effective depth as the distance from the compression face to the area where we have the depth where we have the reinforcement. You will remember that maybe this has been highlighted to you, maybe not. Okay, that the stress block for concrete is a shape that has not really been agreed upon universally by the engineers and scientists who have studied concrete in bending. So this shape that I've drawn, it varies from one standard to the other. If you pick the British standard, you find the shape is slightly different. If you pick the Eurocode, you might find that the shape might be a bit different. If you pick the Chinese standard or the Japanese standard, this shape would be slightly different. And that is part of the reason why things like this equation here, which you must have come across at some point, 0.156 FCU BD squared. The variation of this shape is what gives rise to the variations of that factor. For example, this is the BS. The Eurocode, I think it talks of 0.167 FCU BD squared. Okay, so these variations of this factor is basically because that shape, stress distribution shape of the concrete in compression for a concrete element in bending has not been agreed upon universally. So most different standards will have a different description of that, and therefore this is reflected also in the design equations. But that is by the way. What I want to highlight to you as a way of reminder is that this concrete here will be under compression, and if we take that stress block and multiply with this area here, we'll get a force of concrete in compression. Force of concrete in compression. I'll repeat that this concrete here is under compression, and this is an assumed approximated stress block. If we multiply the stress with the area of the concrete in compression, we get a force, and that force is called the force of concrete in compression. Similarly, the reinforcement steel, which is provided here, will generate a force to resist or to to match the force of concrete in compression. We call it the force of steel in tension. Now, these two are usually separated by a perpendicular distance that we generally refer to as the lever arm. And for you to design a concrete section, you need to ensure that either that couple or that couple are greater than the applied moment. This is just a recap of the reinforced concrete design, which you guys have done. Okay, so we have an applied moment, and for us to determine this reinforcement, we would have used this approach. So this equation FCC multiplied by LA is a couple. So FCC multiplied by LA is a couple, or FST multiplied by LA is a couple, and both of them have got to be greater than MA. Now, with that understanding, therefore, with that understanding, I should have called this aside so that we can follow the thought process. So this was aside. Okay, so now I'm continuing with the calculation using the brown pen that we have been using. So then we can say from here that the applied moment should be equal to at least I'm picking this expression here, I'm picking this pattern. So when you design the reinforced concrete, you check the concrete and in compression, the two equations that I've just written for the BS and the, that equation there. 156 FCU BD squared deals with this. And then AST, I'll write them here and I'll leave them here when you're revising, so that you can be remembering. Okay, so that deals with that. And this other equation here, AST MA 0.87 FYZ, that deals with that part. Okay, so I'm just pulling out this scenario, and I'm saying that the applied moment cannot exceed the internal moment of resistance, courtesy of the steel in tension. I like saying too many things. Just allow me to say this. This internal moment of resistance due to concrete in compression. And this becomes, this one here is internal moment of resistance due to steel in tension. We want to isolate this equation here, to say if this internal moment of resistance was equal to the applied moment, what kind of stress would the steel be experiencing? I'll repeat. We are using this equation to answer the question. I'll even write it here. We are using this equation to answer the question. At the applied moment value. MA. What is the stress in the steel? The reinforcement steel. The force of the steel in tension is basically area times the stress of the steel. This force here is basically just the area of the steel multiplied by the stress in the steel. Okay. Area of steel stress in the steel. And that's what we want to use. So therefore, that equation of MA becomes MA is equal to AS multiplied by Fs. We're just substituting FST with AS and Fs multiplied by the lever arm, or Fs simply MA divided by AS LA. That equation, now I've shown you where it's come from the very basic principles of the design of reinforced concrete structure. This equation, I'm putting in a box. This equation, this is the equation that is used. This is the equation that is used to calculate the stress in the steel reinforcement. I pause here and I go back to remind you why we are even bothering to calculate the stress in the steel section. Why are we bothering? Because if we can find the stress, we can find the strain. If we can find the stress, and we know the Young's modulus of elasticity of steel, we can find the strain in steel. That is why we bother to calculate the stress. This is where we started from. If we can find the stress, we can find the strain. And why are we bothering to calculate the stress? Because we want the strain. We said the basis of calculating cracks is basically how much strain goes into the concrete. This is the thinking. That's why we're bothering to calculate the stress in the steel. You see, the concrete will crack at the bottom because that's where there is tension. And that's where we're putting the steel. So if we can find the stress in the steel, we can find the strain in the steel, and that strain now we can use to calculate how much strain the concrete undergoes. Okay. The lever arm is usually approximated. We are continuing with the calculation. The lever arm, so that we can have the lever arm value here, is usually approximated as the depth of the section minus x over 3. Remember, we have calculated x. We've calculated that value there, x. So this is according to the BS. If you pick the Chinese standard, this equation will change a bit. This equation here will change a bit. Or if you pick the Eurocode, maybe it might change a bit. Okay. Why is it changing? Again, I'm reminding you, please, you'll allow me to keep reminding you, the stress block assumed keeps varying from one standard to another. Okay, so for the BS, this is the equation that approximates the lever arm after we've calculated the x value. So this then becomes is equal to 300 minus the X value we had calculated is 112.3 divided by 3. And this gives us the value 262.6 millimeters. This is the lever arm. So with that now, we can calculate the stress in the steel. Therefore, the stress in the steel, therefore, the stress in the tension, in the tensile reinforcement steel will be Fs. We're just borrowing that equation there. MA divided by AS LA 156.5. You remember this is our serviceability limit state bending moment. This is our serviceability limit state bending moment. Okay, that value there, which we calculated right at the beginning of the calculation. So because cracking is a serviceability limit state consideration, we use serviceability limit state loads. That's why we do that. So because it's in kilonewton meters, we convert it to newtons millimeters by multiplying by 10 to the power 6. Basically, we multiply that by 1,000,000. Then how much reinforcement is provided? It was 2512. This was given as part of the question. And then what is the lever arm? We just calculated it as 262.6, and this value becomes 237.6 newtons per millimeter squared. So we are saying this. There's a bending moment that is trying to bend the wall. There's a bending moment that is trying to bend the wall, and we've put reinforcement near this face to prevent these cracks here. We've put reinforcement on the inner face of the box culvert to prevent these cracks that I've sketched there. So how much stretching is the reinforcement that we've put feeling under the current loading, that bending moment that was defined? How much stretching, how much stress is the reinforcement feeling? This is the number. This is the stress. This is the number. This is the stress that currently under that applied moment, with the depth of this section, with the thickness of this section, it actually feels 237.6 newtons per millimeter squared of stress. With that stress value, then we can now come and borrow from this equation here, which we wrote a bit earlier. We can come and borrow from this equation. Young's modulus of elasticity is given by stress over strain. So if we want strain, we simply say it's stress divided by the Young's modulus of elasticity. So that's how we find the stress in steel, and that's the next step of this calculation. So we write here to calculate the strain in steel. So strain in steel is simply the stress in steel divided by the Young's modulus of elasticity of steel. It's 237.6 divided by 200,000. This should give us 1.19 times 10 power -3. Strain does not have units. You notice that the units for stress simply just cancel out with the units for the Young's modulus of elasticity. So it's just a number, pure number without any units. So now we have gotten to a point to say this in this section here, the reinforcement is stretching by a certain amount. And because the reinforcement is bonded to the concrete, at the point where the reinforcement is, the concrete is also stretching by that amount. Consistent deformations. If you can remember the thoughts of consistent deformations, because the concrete is bound to the reinforcement. When the reinforcement stretches, the concrete also stretches by a similar amount. So by calculating the strain in the steel, the reinforcement steel in this section, we have basically also calculated the strain of the concrete around the area where this steel is. Then we are asking ourselves, the cracking doesn't occur there, it occurs at the edge here. The cracking doesn't occur there, it occurs at the edge here. So how do we calculate the strain of the concrete at the edge, the outermost fiber? So that's what we want to calculate next. So we'll redraw this section. We'll redraw this section and put in the numbers. Let me draw it here so that we are clear. We've got our section. Draw it a bit longer. Just exaggerate the height a bit here. Then of course we have calculated the position of the neutral axis. It's somewhere, and we'll put the value of that number there somewhere. Okay. And the stress block looks like this. That there is tension, and then there is, at the neutral axis, it becomes compression. I've drawn this badly. Let me move the neutral axis so that it falls right where the stress changes from tension to compression. Neutral axis is somewhere there, like that. Okay. The depth of the section, you will remember, is 350 from top to bottom. The depth of the section is 350. So we'll write here 350. The neutral axis depth, value of x, we have calculated it as 112.3. 112.3. Of course, we know that this part of the concrete is under compression and the rest is under tension. The question we have been given tells us that there is reinforcement here, and it's placed about 50 millimeters from the edge. Concrete cover is about 50. So we also have this dimension here. We have this dimension here, and it's 50 millimeters. So this value here is 50. Okay? So we can calculate this value from the neutral axis to the reinforcement, and it looks like 187.7. We have the concrete cover, and we have the depth of the neutral axis, so we can calculate this value of 187.7 from the total depth, which is 350. Now, we're coming back to this section here. If we assume that the stress, the strain on this cross section is linear, the way we have drawn it here, then we can work out how much the concrete strains in compression. can work out how much the concrete strains in compression. We are not interested in that. We are not interested in how much the concrete strains in compression. What we are interested in is how much the concrete strains in tension. All right, I will highlight this one here to say we are interested in how much the concrete strains in tension, because that's what will cause the cracking. Now, just to remind you that we have calculated a few minutes ago successfully this value here. We've calculated successfully this value here a few minutes ago. This is its strain in steel. We've calculated it as 100 at 100 by 1.19 times 10. Calculate it as 1.19 times 10 to power negative 3. I'll write a note here that from similar triangles, which you guys did successfully and passed in secondary school, we can calculate the value of ECT can be calculated from this stress block, strain block, strain, not stress, strain block. How? Let me isolate the triangles. So we got, how do I use? We got a triangle. No, let me use a darker pen. Yeah, green is good. We got a triangle like that. From the neutral axis to this point here to this point here. Okay. The depth of that figure is 187.7. And this value here is given as 1.19 times 10 minus 3. That's the first triangle. Then we've got another triangle, bigger. The depth of that triangle is, okay, so the second triangle we extract from the neutral axis to this corner and to this corner. So the depth will be 187 plus 50. Okay, 187.7 plus 50, so 237. 237. To write it properly so that you can not good. 237.7. Okay, and this value here is what we do not know and we want to find out. This value here is what we do not know. From similar triangles, Very easy. Okay. So just for the sake of making this calculation complete, therefore, we can calculate the strain just from similar triangles. Strain in concrete, in compression. We've said we really don't need this for crack calculation, but some standards call this EC1. And some standards, those standards also, if they use numbers, they call this EC2. So that's what I'm referring to here. EC1 will be, you'll check these numbers later. It's just a simple calculation of those similar triangles things. 10, -4 in compression. Then strain in concrete in tension. Which we can call EC2, is given by 1.15 or 1.51, sorry, and -3. So if you work out these two triangles, you find this value here is 1.51, 10 minus 3. Okay, which is this value. Yeah, we can push this and finish it. We've come to this. We finished this this document. So you'll allow me just 1 minute. I create another one so that we can finish this calculation. I'll save this new file as B. Then I'll open it so that we continue using continuous scribing. So there we are. So I'll put today's date again, so that you can connect 11/20/23. Now we know how much the concrete is stretching at the bottom, courtesy of the tension there. So the reinforcement is resisting it, but the reinforcement, because it is stressed, it's also stretching a bit. So with that, and using similar triangles, we've calculated how much the concrete is trying to separate, is trying to stretch at the bottommost, because when you bend an element, bottom becomes under tension and the top under compression. So that's where we are, and we now we want to conclude the back calculation. So the crack width is given by this value, with this equation. So if we have the section which I'm drawing, and I'm drawing and I'm doing a blow up, so that we are only seeing 2 reinforcement bars, because cracking will occur between two reinforcement bars. So let's assume it's continuing this side, it's continuing this side, and it's also continuing that side. So we're not drawing the whole depth of 350. And then we got these two bars, exaggerated. So these two bars. These two bars. From the question, we have been told that the spacing of this reinforcement is 125. You can move the date a bit. $125. We put the date as 20th, 11, 2023. Okay. And we have also been given this dimension here. This dimension here, from where the reinforcement is to the edge that we are interested to check the cracking. This is the concrete cover, which we have been given as 50 millimeters. The place likely to crack is the farthest point from the two bars. So it's somewhere there. I'll write a note here. The place most likely to crack is the farthest point from the two bars. The farthest point from the two bars, and that's where we want to calculate how much cracking would occur there, because that's where the worst case cracking would occur in this structure. And the distance from the bar to that point is referred to as ACR. What do we use? Let's use the purple. So this distance here, which is the distance, the maximum distance possible from any bar to the farthest point that you can have, the center of the bar, is referred to as ACR. And because the bars are spaced at 125, so this dimension here, the maximum possible dimension away from the bar, would be a half of 125. So this value here will be 62.5 millimeters. This is the farthest possible, that 62.5 millimeters. Okay. So ACR, the value of ACR using okay, because we are having this kind of situation. We are having that. So if that is A, that is B, that is C. So we say A squared is B squared plus C squared, or A is B squared plus C squared square root. Using that, let me use a different color now to do the actual calculation. So ACR, therefore, will be simply square root of the vertical distance to that which is 50 squared, plus the lateral distance to that point where the crack is most likely to occur, which is 62.5 squared. Okay, so these two, we square them and then we do a square root of that. And then, because the reinforcement bar we are using is 20 millimeters, and we have measured ACR from the center of the bar, so the surface of the bar, which is what we are interested in, will be 10 millimeters closer to the point where it's likely to crack. So that's why we subtract. Let me put it correctly. Subtract 20 over 2 so that you can remember. 20 over 2. And I'll say bar diameter here. Bar diameter. This is the bar diameter. Bar diameter. Bar diameter. Okay. So with that equation, we can find SER is 20 millimeters. Now, at this point, there is an array of equations that have been suggested to give us the crack size. The BS suggests 2 equations. I will not bother with both of them. One is simpler than the other one, and is the one that I will present here in this class. If you're interested, you can go and read on the others as well. So the crack width to BS is given by CW is equal to 2.3 multiplied by SCR, which we have calculated, multiplied by the strain in the steel in tension, what we have called EC2. That's the equation that calculates. That's a simpler equation for calculating cracking. Okay, so strain in concrete in tension we have calculated earlier here. This value here, calculated it. SCR we have now defined it and calculated it, 70. So we just plug in these values. So 2.3 multiplied by 70 multiplied by this number here, which is 1.51. Multiplied by 10 to the power -3. That gives us the crack size as 0.243 millimeters. Allow me to do a recap from where we started to this point where we have a value for the crack size. Allow me to do a recap very briefly, maybe 1 minute, so that we can try and make it flow. So we started by saying the general theory of bending suggests that when an element is bending, part of it, one side will be in compression, the other side will be in tension. That's where we started from. And we said, for this equation, we can actually calculate how much stress is felt at any point on that cross-section using this equation. M over I is equal to sigma over y, which you dealt with in your strength materials. Then we went ahead and said, if we can find the stress sigma, then we can find the strain. We can find the strain. And when we got to that point, we said that strain is the basis for determining how big the cracks will be in concrete that is subjected to bending. When we got to this equation for strain, we said the strain in concrete is the basis for determining how large or how wide the crack will be in concrete. Then we went ahead and started on an example. So we picked this example here. And we say because cracking is a serviceability limit state problem, we convert the applied ultimate limit state moment into a serviceability limit state moment. That was the first thing we did in the example. Then we said that now that the concrete and the steel are not perfectly elastic and perfectly isotropic in that section, the neutral axis is not necessarily at the center of that section, halfway down. And the neutral axis, we said, is affected by these two factors, rho and alpha. Then we've gone ahead and calculated these two factors, rho and alpha, and we've used them to find the value of the neutral axis x. So we found that for this particular problem, where the wall is 350 thick, the neutral axis under the bending moment applied and the reinforcement provided is at 112.3 millimeters from the compression face. Then we have stepped aside a bit to remind ourselves the theory of bending, of the design of the reinforced concrete element in bending. Then we've gone ahead and picked the equation for the internal moment of resistance due to steel in tension, and we've used that equation to find the expression for calculating the steel stress when the element is in bending, and we've put this reinforcement. So we've actually calculated the steel stress as 237.6. Now, remember we had said that if you can find the stress, you can find the strain. So with that stress, we were able to find the strain in steel, and we've come then to draw the section so that we can then calculate the other strains. So we've drawn the section with all the relevant dimensions, and we were able to then, using similar triangles, find the strain of the concrete in compression and the strain of the concrete in tension. After that, we have gone ahead to calculate the dimension SCR, which is the maximum possible distance from a reinforcement bar to the surface that we are analyzing cracking. We have calculated that value, and for this particular case, we have seen that that value is 70. Then we've used one of the equations recommended by the BS, and we've plugged in these numbers, and it has given us a value of crack of 0.243 millimeters. In physical terms, what that means is that if this structure is built and is reinforced by the reinforcement as specified in this example, and if the moment applied does not exceed what was given again in this example, this value here, this value is 234.8 kilonewton meters per meter, then the crack size cannot exceed or will not exceed 0.243 millimeters. This is how you calculate a crack. Now, I want to say maybe one or two other things about cracks. Now, we're not calculating anymore. I'm just saying why we bother to calculate cracks in concrete. We started by saying, when we started this concept, you said that reinforced concrete will always crack. When you have a reinforced concrete element, be it a beam, slab, wall, or anything, it will always crack. The concrete elements that do not crack, or we can design them so that they do not crack, are pre-stressed concrete elements. So it's possible to pre-stress concrete so that even during its service life, it will never have a crack. So the crack size will be 0. It's possible to design in pre-stressed concrete. But for reinforced concrete, always you'll have some cracking. The standards limit the size of these cracks depending on the purpose for which the concrete is made. I'll repeat. The standards for design of reinforced concrete structures put limits on how much crack size you can allow on a particular structure based on the purpose of that structure. So I'll give you two examples. If you're designing a water tank, a reinforced concrete water tank, which is where we came from, the previous topic, we did an overview of water tanks. So if you're designing a reinforced concrete water tank, now we know that concrete will always crack. Concrete will always crack. So therefore, we need to check, after we've designed and put in the reinforcement, we need to check how much the crack is. We need to check how much the crack is. And if it's not big, we need to change some parameters, which I'll talk about shortly. For water retaining structures, I think the BS talks about a limit of 0.15 millimeters. For water retaining structures, the BS, I think it talks about 0.15 millimeters. A very, very tiny crack, but it's allowed. If our concern is the durability of the structure, for example, when we design bridge structures or box culverts, the standard gives guidance to say that for bridge structures and water retaining and the culverts and basically road structures, road drainage structures, because of the continuous passage of water, so the crack size must not exceed 0.25 millimeters. 0.25 millimeters. That is why this calculation was stopped here, because this wall is a culvert wall, and the crack size that was calculated was found to be lower than the maximum allowable, which according to BS, I think, if I can remember properly, is 0.25. Okay. So now I want to write some of these thoughts that I've just shared, so that you have them as part of your notes. And then we will close this session. I think I've said too many things. So write them in orange. The standards. For the design of reinforced, or the design of reinforced concrete elements, do specify different acceptable crack sizes, crack width is better English. Crack width for different applications. E.g., for liquid, retaining structures, the allowable crack width would be smaller than for, say, durability considerations, durability considerations. So once we calculate the crack size, we need to ask ourselves, does it meet the standard requirements for the purpose which we are designing this structure to serve? The other important thing that I want to mention, in the event that the calculated crack several things could be adjusted. The first one is you could reduce the spacing of the reinforcement. First one, you could reduce the spacing of the reinforcement. Reduce sorry, thereby reducing the value of SCR, thereby okay, so let's just go back to this sketch that we just looked at. So if we were to find that, for example, the crack size is exceeding 0.25, for example, we could decide now to work with a smaller bar. Instead of, say, 20 millimeter diameter, we could change to a smaller bar and then reduce the spacing. So therefore, we provide the same amount of reinforcement. And I'll give you an example shortly. By reducing the spacing of the bars, the value of SCR reduces. And by reducing the value of SCR, the crack width, which is proportional, direct proportional to SCR, also reduces. So that's the first thing you could do. And I have here with me an example, e.g., this problem that we have looked at, we were working with T20s at 125 centers. The reinforcement amount that we're providing with that for every square meter, or for every linear meter, is that we could say, why don't we try T20 at 100 centers? So SCR reduces, but then the reinforcement increases to 30, 40, so it becomes less economical. Or you could say, let's try T16s at 100 centers. This is not a very good example, but it shows you 2010. So if we could reduce the reinforcement size and the spacing such that we achieve similar amount of reinforcement, then that would be a good solution. That would be a good solution. For example, though this is not a good example, you know, if we put, for example, T16 at 75 centers, the reinforcement that we'll be providing is 26, 79. It's very close to what the ultimate limit state wanted. So we're basically not increasing the reinforcement, we are only reducing the size of the spacing, and therefore reducing the size of the crack. The second thing that you could do, if you found that the crack size is bigger than what is desired, you could reduce the tensile strain in the concrete. I'll explain. That is EC2. By simply reducing the tensile strain in the steel. By simply reducing the tensile strain in the steel. So how would you do that? One, you could increase the depth of the section. Okay, by increasing the depth of the section. Increasing the depth of the section. Let me show you. It's important that you are able to make sense of all of this. I want to go where we are calculating the. You notice that if the lever arm was to increase, the stress in the steel would reduce, and by extension, the strain in the steel would reduce, which is the easiest way to increase the lever arm. Make the section thicker, make D bigger. That's what this first point here. It's saying, or you could simply increase the amount of steel reinforcement that you're providing, increasing the amount of steel reinforcement provided. Again, just from this equation, if you increase the amount of steel, the stress in the steel reduces. If you increase the amount of steel, the stress in the steel reduces, and by extension, the strain in the steel reduces. That's the second thing that you could do. The third thing that you could do could increase the strength of the steel. You could increase the strength of the steel, but this is not a very common approach. Right, even in blue, not very common. Not very common solution. Not very common solution. Because it's not practical for most problems that you'll encounter. With that discussion, I want to ask you to try out these two problems as part of the assignment. Calculate the crack size. Calculate the crack size. The crack size if the concrete section was 300 millimeters. Thick instead of 350. Section as discussed above. In the example. All other terms remain as they were. So the loading, the strength, the Young's modulus, the strength of the concrete, everything remains as it is. And then part 2 of that assignment, I want you to repeat question 1 above, section of 400 millimeters thick. This is what I wanted to present to you on the front of the crack, and you'll agree with me that with the noisy environment we were having the other day, it would be next to impossible to even pass my thoughts to you. So now I want to allow, if somebody might have a question or a comment, you can ask. My preference is that you look at what we have discussed, make an attempt of the questions, then you will have better questions to ask. You'll have better questions to ask once you have just gone through the problem and you've attempted these assignments. You'll understand better, and then your questions will be a bit more informed. But still, you have a right to ask if somebody would like to ask something. Yes, please, you can ask. Yes, Kabonye.
When you're calculating ACL, you have said the reason we are using half the diameter minus half the diameter is what?
The 30,000, is usually a measured stress-strain relationship for concrete. The 30,000 is usually laboratory measured. And for laboratory measured test setups, you cannot set the test to run for 10 years. So it's generally referred to as a short-term Young's modulus of elasticity of concrete. What we need to use is a long-term Young's modulus of elasticity for the concrete, because the concrete element, like a box culvert, will stay there for many years. So generally, it has been accepted that the long-term modulus of elasticity for concrete is basically about 50% of the short-term modulus of elasticity for concrete. That's why we apply the half. Any other question?
I meant when calculating ACR.
ACR.
Yeah.
No, it's a bar size. The 20 is bar size, and we are dividing it by 2 so that we remove the radius. That's your bar. We've calculated that. But the distance we want is that. This bar is 20 millimeters. So we subtract half of that so that we get this distance, because it's the one we want. This one is the one we want. I'll allow one more question. It's just about 1 o'clock. One more question, and then we can stop there. I need one or 2 more lectures. In the meantime, we need to agree when we will do a timed CAT, because we have to do one. We have to do a timed CAT, and then I'll collect these assignments and I'll mark them as part of the coursework for this unit. It's a design unit, so 60% is basically coursework, the assignments and the CAT. Any question? Great. So thank you very much. Class rep, please, you check where we can have one more session. Sorry, this particular unit, I've struggled a bit because I seem to have a lot of other things that need to be done, and I had not foreseen this when I was taking up the unit. So it's a bit pressed, but we are just about to wind up. So thank you. Have a good afternoon, and we meet again in the next session. Thank you.